All right, so up to now we've talked a little about propagation, we've talked about noise, receive power. What I want to do in this section is to quickly give you some tools to relate that to how your system will perform in a real setting, so to understand how that can, whether your system can meet the requirements that you need. So when we think about requirements, really there are multiple different dimensions that trade off between one another in different ways. So first of all, obviously in any communication system, we want to transfer an amount of rate. So the higher amount of data rate we can transfer, the better. But that signals, or particularly wireless signals, will occupy some bandwidth, which is typically limited. We also, when we get that rate, we want to talk about the reliability by which we get this. And finally, somehow the channel quality that the signals will be getting transmitted on. And somehow there's a trade-off between all of these, and what I want to do in this section is to talk about, give you the tools to understand how to measure each one of these, and also to understand their relationships between one another. So let's, before to do that, let's go and review the basic steps that we see in any practical transmitter. So typically we can think of transmission as occurring in multiple stages. The first is that we start with some information, and then we usually typically perform some kind of channel coding to get coded bits. We would then modulate those into complex symbols, and then we would usually do some kind of transmit pulse shape filtering and digital D to A conversion, and then finally an up conversion before we modulate that onto an antenna. The first two parts of this, the channel coding and modulation, typically called the modulation and coding scheme, which I'll talk about more both in this section and the next unit. Now, each one of these stages are typically characterized by different parameters. You have some information rate, which will be the product of the coding rate times the modulation, which is the number of bits per symbol, times the number of symbols per second. I'll give you many examples shortly so you get an idea of the typical parameters that we're dealing with. The signal bandwidth will be typically, we'll denote by fs, which is 1 over that symbol period, but the occupied bandwidth might be a little larger because there's usually some excess bandwidth associated with the filtering. And finally, we have a term what we call the spectral efficiency, which is the rate per unit bandwidth. If these are unfamiliar with you, just go back and review any digital comm class. There's also a GitHub link that I have for the digital comm class when I teach it, but there's many references that you can get. Okay, let's just do a sample calculation just to review to make sure that you understand all the concepts. Suppose that the channel coding is 1/2, and we use 16 Comm. Right, and 10 megasymbols per second with an excess bandwidth of 10%. So when you look at numbers like this, that means that the code rate's 1/2 and the modulation is 4, because there are 4 bits per symbol, because it's 16 Comm. Sample rate is 10 megasymbols per second. So the information rate will be just this product, because we have half a coded bit per half an information bit per coded bit times 4 bits per symbol times 10 megasymbols per second. That gives you 20 megabits per second of information rate, and the occupied bandwidth will be just a little higher than the symbol rate. Okay, so that's very easy calculation to do. Now that we understand information rate, let's go on to the next key requirement, which is reliability. So typically for reliability, we think of most communication systems that transmit data in blocks, which are related to the block length. And those numbers can range between the hundreds up to tens of thousands. And that may or may not be aligned with the higher level packets like IP packets. Now, whenever you have block transmissions, we can think of reliability in two ways, and we'll use both in this class. One is the bit error rate, which is after you decode it, whether it's an individual bit is in error or not, or the block rate, which is typically more common, which is that the whole block is in, there's at least one error in the block. All right, what is the appropriate level of applied reliability will depend on the higher layer protocols. So usually most protocols have some mechanism of detecting errors, and then we'll go back and try to retransmit in the presence of those errors. or they could be corrected at the application. In about 2 units, we're going to talk about this in detail, but I'll just say for now that those requirements will be determined by what we do at those higher layers. All right. The next important way to think about requirements is the signal to noise ratio, which we talked a lot about in the previous section. And if we have our system that we've been dealing with up to now, remember we can talk about the SNR per symbol, which we mentioned before, which is the received power times the symbol duration divided by n naught. But it's also sometimes better to normalize that by the data rate. And we can think of that as the SNR per bit. All right, and the SNR per bit will best be the received power over N0 divided by the rate. And this has, it's called EB-NO, or that's how it's at least pronounced. And the requirement will depend on the MCS and that quality of the receiver. So let's just do an example, which is pretty common. So I took this from Propagation's book. So what this shows you are different lines of the different probabilities of error, all right, as a function of the EB-NO for different codes. And so let's just say I'm going to use a convolutional code with a constraint length of 5 and a rate 1/2 and 16 Comm. And I give you the symbol rate, and I give you the transmit power and the received noise power spectral density. And I want to get a bit error rate, say, of 10 to the minus 4. All right, and I want you to find the maximum path loss. Well, that's pretty easy. So what we do is I say, okay, 10 to the minus 4 is here, and I'm going to use this code, which is this line here. That's the constraint length 5, and it needs about an EB-NO of about 4.5 dB. All right, so that's that. The information rate that I would be getting if I could transmit this would be the code rate, which is 1/2 times modulation, because 16 Comm times 100 megasymbols per second. So in this case, we'd be getting about 200 megabits per second. So it's a very high-speed link. All right. Now remember that the EB-NO is the received power divided by N0 times the sample rate. Or in dB scale, we could write it like this. And so now I can say here that the received power has to be this EB-NO plus this rate plus the thermal noise, and again in this case they have to have minus 82.5 dBm according to this graph here. So since we subtract the transmit and receive power to get the path loss, that gives you that the maximum path loss in this case would be about 105 dB. All right, so that's how you do a typical requirement. All right, so the requirements we saw on the previous graph were for a particular receiver, in this case a convolutional decoder. But one thing that's important to think about is what's called the capacity, which is the maximum rate achievable given some bandwidth and SNR requirements over all possible communication schemes, even communication schemes that may not be practical to actually build. That maximum limit is called the capacity, and is given by the famous Shannon formula, which again would be reviewed in your digital comm class. And it relates in some very simple way the maximum capacity to two key quantities, the bandwidth, B, and the SNR, which I've written in this case as gamma. Remember that this should be done in linear scale if you do this. If you divide the capacity by the bandwidth, you can also think of Shannon's capacity formula as giving a maximum limit on the spectral efficiency. This goes back to this very classic paper from the 1940s. All right, so here it is graphed if you don't remember it. So in this case here, I've drawn it written as a function of the EB-NO on the x-axis, and here's the capacity on the y-axis. And you can see this increases as follows. Now, when you look at this graph, communication theorists like to think of their two key regimes. In the low SNR regime, it's what's called the power limited regime. So in this case, imagine that the bandwidth goes to infinity, but if the bandwidth goes to infinity, you have this term going up, but this term going down, and then when you take the limit, you get that the capacity is just given by this simple formula here. And in this case, you can see that for very low SNRs, or equivalently when the bandwidth is very large, relative to the transmit power, then the capacity scales linearly with the SNR, or equivalently linearly with the power. So that's this regime here. On the other hand, when the SNR is very high, or the bandwidth equivalently is very limited, you'll see here that the capacity is approximately log of this SNR. So in this case, the SNR continues to improve the capacity, but at a much, much slower rate. And you'll see in practical systems that actually the rate improvement with SNR is even more limited and generally kind of saturates. So this would be in this case, this regime here. So this will typically correspond in practical systems to transmitting at higher modulation and coding schemes. Also shown on this graph are typical simple uncoded systems here of different modulation orders. You can see they're quite a several dB away from the capacity limit. Okay, as I said, the Shannon capacity is kind of a limit over all mathematically possible systems. In reality, you can't ever achieve it exactly, although we can get quite close, because it requires both infinite computation and typically infinite delay. So most systems, of course, get some number below the Shannon limit, and one way to describe a practical system is with a formula like this here. In this case, we say that the rate is very similar to the Shannon capacity, excepting there are two kind of correction factors. There's a pre-log term here, which is related to basically a decrease in the bandwidth. That can occur physically because there may be overheads like pilots or other guard intervals in the system, as well as kind of a decrease in the SNR by this factor beta here, and that can be due to receiver imperfections. And usually the capacity loss is typically at least 3 dB in most practical systems, particularly, say, in the cellular space. All right, let's just do a quick example to make sure you understand the concepts. Suppose I say that the system has 20% overhead, certain bandwidth in SNR, and it operates, I say, 3 dB below the Shannon capacity. And then I ask you, what is the rate for that system? So we're going to say, well, if it's at 12 dB and it's going 3 dB below capacity, it's kind of effectively an SNR of 9 dB, or 8 in linear scale. And so therefore the rate is our Shannon capacity formula with the effective SNR and this fudge factor for the 20% overhead. And when you plug it all in this case, you would get 25.3 megabits per second. Just remember that in units here because that was in megahertz. All right? So just the units. Just have to be careful. It's not hard. Okay. Putting it all together, often you get up with what you put together what's called a link budget. And the link budget will usually be some kind of table like this. So you start with some transmit power, let's say in this case 23 dBm, which is, as I said before, kind of the typical transmit power from a mobile device. I would have some distance-based path loss, all right? And in this case, it's 90 dB. We know how to compute the distance-based path loss in free space from Unit 1. And later in this unit, I'm going to show you some ways to compute it for other types of environment. In this case, let's say there's some shadowing for obstructions. We'll talk about this in the next section. And so then taking the transmit power and subtracting these, you get this minus 87 in this case of the received power. Then we take our bandwidth and the noise figure. That will depend on your receiver. And that will give you your noise power. And then we can compute the SNR. So some kind of tabular accounting, if you like, this budget where you start with the transmit power, look at all the losses, and finally end up with your SNR. And then depending on the MCS that you're using, you can then predict what kind of rate that you would be able to get and whether you have sufficient SNR for the reliability you need. All right, if you go to the demos, I've put in a quick, very simple MATLAB demo here to show you how to do these. So in this case here, I have some parameters like the bandwidth, the carrier frequency, noise figure, also some parameters for the link layer model, which describes the rate as a function of the SNR. And then I just look in free space, I look at a set of distances, and then I compute the path loss for each of these distances. Then I can compute the symbol SNR, the SNR per symbol, and they can compute the effective rate that you would get as a function of that SNR. So when you plot it here, we see our distance, and we can see that predicted rate that we would get. So if we're very close, we can get almost 70, 80 megabits per second, but then it starts to decrease. In this case, in this particular link layer model, there's kind of a maximum spectral efficiency that you end up with because there's a maximum MCS that you would actually have. So go ahead, check that out, but it's a very simple, short piece of code. Okay, that wraps up this section. What I want you to try to do is the second problem. Again, all the in-class problems are in the GitHub link below. So this table comes from a 3GPP document. 3GPP is the standards organization that builds your cellular standards. In this case, this is LTE. And they've actually shown, in this case, the spectral efficiency for different codes they use in this system. These are very sophisticated codes called turbo codes, which I might have a chance to talk about a little bit later in subsequent units. So for every SNR, there's a spectral efficiency both in the uplink and the downlink, which account for all the other imperfections, and they're plotted here. So actually, you'll go ahead and you'll plot this, but you'll also plot the Shannon capacity, and then I'm going to you to fit a model for this SNR to rate mapping based as some decrease from the Shannon capacity. So give that a shot, and once you're done, you can go on to the next section.